So the first things I outlined in my code are the source charges. I labeled them as B1, B2, and B3, making sure to position and color code them accordingly. Since the first charge is positive, it's going to be a red ball right here. And since its charge is smallish, I made the radius small as well. The other source charges are blue because they're negatively charged. And again, I placed them where they should go at 750 and -5, -90. Notice that I've also defined the charges of each of the balls in these lines right here at 4, 7, and 10. And here are the 10 points that I will be examining, and they are magenta dots all over the plane, as you can see here. I'll comment them out for now because we'll look at some of them individually later. This section, I've defined K, which is 1 over 4 pi epsilon naught in the equation for electric force, here as 9 times 10 to the 9, and my scaling factor is 0.0001, so that the image I code for shows up nicely. Here, to make the grid of points, I defined I and j, which are analogs for x and y in vector form, by telling GlowScript that I want the scale from -20 to 20 with an increment of 1, meaning that there are a total of 40 points in the I and j directions. To code the electric fields for each point charge, we have to use the equation E equals 1 over 4 pi epsilon naught, or k, times q1 times r hat over r squared. But first we define our r, which is the displacement vector, which starts from the point charge and extends to each point on the grid, which is why we have vec ij0 as the final position. This way we can have the electric field vectors on every point in relation to the source charge. And now we can define what our E field is for each point charge by multiplying k, the source charge, and r hat, and dividing by the magnitude of r squared. And since we have multiple charges on this plane, we want to know what our net electric field is, so we can have vectors that reflect the influence of all of the source charges. We do this by adding up all of the individual electric fields together, as you can see here, and we can visualize vectors by using arrows at each point on the grid. The axis is defined by the net electric field, but multiplied by our scaling factor so they all look nice, with a small shaft width so we can see everything clearly. And so now we can see what this whole thing looks like. You can see that the electric field vectors emanate from the positive charge and feed into the negative charges right here. It even looks like they bend in order to accommodate the forces they're experiencing. And in relation to the original problem we have, we want to know what the vectors look like at 10 different points. So let's say, for example, we want to look at point 3, which is at -3, -6, 0. And so if we run the program, we can see that it lies right here, and the arrow, which represents the electric field emanating from this point, is pointing towards the negative charge at -5, -90. If we want to look at another point, say point 5 at 220, it's about right here, and we see this arrow, which isn't that obvious, but it's this one, and it's also pointing towards the other negative charge at 750. And you can see it appears to be emanating from the positive charge, and it's bending towards the negative closest to it. And so we can see what the electric fields look like for all of the points. As you can see, the length and direction of these arrows depends on the relative location of each electric field vector in relation to the source charges on the same plane that are influencing them.